Okay, then, so welcome everyone to today's presentation hosted by the Southeast branch. Um, we've got a presenter, Ken Lax from Corroconsult today, and he's going to present on cathodic protection, monitoring and maintenance. So if you've got questions throughout the session, can you please put them in the chat? We're going to answer them in the end of the session. This session will be recorded and will be available on the Pipeline Industries Guild YouTube channel. And I think just a housekeeping, can you please switch off your cameras and mute your microphones so we've got best quality of the presentation. So I think that's it from me, and then over to Ken.
Yes, good afternoon, good morning, everybody, wherever you happen to be in the world. Thank you for joining us. As Gosia said, we're going to talk about cathodic protection, monitoring, and maintenance. This is a presentation that's been prepared by myself and Richard Lindley, who is our in-house expert on all things related to field works and pipeline surveys. So he'll probably be the one giving you any detailed answers on the questions that come up about the survey techniques. This is the sixth presentation that the Southeast branch have done of the Pipeline Industries Guild relating to external corrosion. And they're all aimed at non-specialists, as is this presentation. You can see a list here of the previous presentations, and they're all available on the Guild's YouTube channel. So if you find that there's anything we mentioned today that you don't quite understand, you may well find the answer in the beginner's guide, because that's a really very basic guide which assumes absolutely no pre-knowledge of cathodic protection, electrochemistry, or electrical systems, electrical circuits. What we hope at the end of this presentation is that you'll have an understanding of what the routine monitoring and maintenance activities are in cathodic protection. And we hope that the people who are watching this presentation are perhaps people responsible for the management of pipelines and need a somewhat better understanding of what's required for the monitoring and maintenance and why we have to do it in any event. Now, I don't know about you, but as on these webinars, I think of questions as the webinar's going on, and then by the time it comes to the Q&A session at the end, I've forgotten what they were. So I would encourage you to, any time during the course of the presentation, if something crops up that you want clarifying, or you want more information on, or if you want to add a correction or some comment, don't hesitate to pop it into the chat, because Gosia will be watching the chat, and at the end there'll be plenty of time to discuss things, and anything we can't answer off the cuff at the end, we'll get your contact details and we'll send you an email with the answers that you want. We find that that system works quite well. Now, principally, this presentation refers to carbon steel pipes. There are different needs for cast iron and ductile iron pipes. And as a general rule, it's not universally true, but as a general rule, cast iron and ductile iron pipes are not cathodically protected as a routine. The reason for that is that the way that the pipes are joined introduces electrical resistance at the actual joint, and the cathodic protection current that we apply doesn't travel all the way along the pipe as we need. So if we want to cathodically protect cast and ductile iron pipes, we have to put an electrical connection between the two sections of pipes, which is very laborious and expensive to do as a retrofit activity. Now, I'm not going to go through the basics of cathodic protection, but I'm just going to tell you that it's an electrochemical activity, and it works by forcing current onto the pipe. And there are two ways that this current can get on the pipe. One is from what we call an impressed current system, where we impress or we force current onto the pipe by using a power source and some kind of inert anode in the ground. And you can use almost any metallic conductor as an anode in the ground. You can use scrap pipe, you can use old copper pipe, you can use old coat hangers. But those types of anodes are very quickly consumed as the current leaves them and flows onto the pipe. So we have special anodes that we use for impressed current, which these days are quite exotic things. They're called mixed metal oxide anodes, which have a special layers on them, which allow it to conduct the current to the pipe, but they don't corrode as quickly. So these days you can get an anode which will last the design lifetime of the pipe. The other way that we get the current onto the pipe is through what we call a sacrificial or a galvanic anode. And that works by virtue of the fact that it has more energy in it than the pipe has. And if you connect two things together with different energy levels, they will try and even out. Just as if you had, you may remember from school in the physics lab, where you put water into two different test tubes, and then you connected them together and the water settled to give the same level in both of them. Well, that's what happens when you connect a high energy thing like a magnesium anode, a galvanic anode, to a pipe, that the anode tries to bring the pipe to the same voltage that it's at. So those sacrificial anodes did work in exactly the same way in terms of delivering voltage as the impressed current anodes. There's only one law which you need to be aware of to understand these issues, and that's Ohm's law. And that's a universal law. And if you think of the voltage, say the battery or the impressed current anode or the galvanic anode, the voltage being what drives the current around the surface, the circuit onto the surface of the pipe and so on. And if you think of the resistance as the opposition to that flow of current, which is the resistance in the soil, the resistance in the coating, the resistance in the pipe, the resistance in the cable back to the power source, that opposes what you're trying to squirt in. And the current is what eventually comes out at the end. So you can see that the current is inversely proportional to the resistance. The lower the resistance, the more current will flow. The less opposition there is, so the more current will flow. And the higher the voltage, the more current will flow, given that the resistance stays the same. So the issue with cathodic protection monitoring and maintenance is that cathodic protections are virtually invisible. The whole system tends to be buried. The pipeline's buried, of course. The anodes are buried. And the test posts and the power supplies are usually a little bit remote from the pipe. In an impressed current system, the anodes could be 100 meters away from the pipe. So it does tend to get forgotten. But like all electrical systems, it's not perfect. It needs to be looked at. It needs to be checked. And when we design a cathodic protection system, we put other widgets and bits and pieces onto the pipe in order to control the amount of current that flows. For example, we tend to put electrical insulation between the pipeline and the above ground installation, the compressor station, the pump station, or whatever it's going into, because above ground installations are normally earth for safety reasons, because people can go in and touch different parts of the steel that are above ground and they could get an electric shock. So we put earthing systems in there. But if we connect an earthing system to the pipe, the electric current would go to the earthing system because it's a lower resistance than the pipe. Because when electric current flows, rather like water, it tends to take the easiest path. That's not universally true, because actually electric current takes every single path. But because of the different resistances in all the different paths, some of the resistance, the current that arrives is very, very small, measured in millionths of an ampere. So we have to electrically isolate it. And sometimes we have to join up with other people's pipelines, and they've got their own cathodic protection systems, and we don't want them interfering with each other. So we tend to put some form of isolation there, usually insulated gaskets or monoblock isolation joints. So the main things that tend to go wrong with the cathodic protection system are due to normal deterioration. You could get weather effects, some slight soil movement that can damage some of the above ground stuff. You can get accidental damage by other people coming along and laying a pipeline, and they haven't made use of the calling up the phone before you dig system that might be relevant for where you are in the world, or they might just have not known about it. So that needs to be checked. The power supplies that deliver the protection current to the pipeline are subject to aging as well, because one of the biggest enemies for any electrical system is heat. And if you get heat, too much heat beyond the design value, it can affect the insulation resistance of the components, or maybe even burn the components out. And then you have to be aware that that's happened. So it could happen and you don't know about it. It could be a lightning strike, for example, and it's temporarily overheated and maybe not being totally destroyed, but just the cable's damaged. And you need to know about that, because it means that if it has been subject to that kind of stress, that it needs to be repaired and replaced, because it might break down later on. We're not immune to vandalism, especially as we tend to use insulated copper cables for connecting to the buried pipe, which I'll talk about in a bit more detail later. So they can be cut and stolen. And of course, test posts are often a target for vandals, as are the power systems. Some of the power systems we put them up telegraph poles out of harm's way, where people can't get at them. And in the countryside, they can be used for target practice. So that's another thing that needs to be checked. Also, the cathodic protection current, as it flows through the ground, you may recall I mentioned earlier that the circuit is from the power supply via a cable to the electrodes buried in the ground, the anodes, which could be 100 meters away from the pipe. It then travels through the ground to the area of the pipe that's ready to receive current, usually where the coating's damaged and the resistance is low. It goes on there and it circles all the way back via the cable into the other terminal of the power supply. So that circuit is what provides the cathodic protection. But if somebody installs some sheet steel piling in the way, that will block the current. Similarly, if somebody buries some scrap metal or a big stone, or we have all kinds of things over the years encountered, that will affect the flow of the current onto the structure. So we need to be aware of all those things. Now, like everything related to pipelines, planning and preconception and thinking of the worst is the best way to manage the risks that you have. And for cathodic protection monitoring and maintenance, the best way to do this is by creating a priority matrix. And this doesn't have to be done by a corrosion specialist or a cathodic protection specialist. It can be done by any person who's familiar with pipelines, who's got any common sense, really. a typical situation, you would take care of the pipeline factors and the environmental factors, and you'd break down your pipeline into sections, because cross-country pipelines can cover hugely different soil conditions and environmental conditions. It's better to break it down. So the first question you ask yourself, well, how critical is a cathodic protection? Does it matter if it's not applied for a week or 2 weeks or 3 weeks or 4 weeks? And very often the answer is no, because if it's a well-coated pipe, you can survive, and there's no electrical interference from railways or anything like that. You could well survive without any worries for a couple of weeks. However, if you've got a rather old pipeline with a poor coating, which is subject to electrical interference, and it's running underneath a nunnery and a hospital, then you might say, well, any failure of the CP is going to have a fairly quick impact. So that's a high risk. The type of coating is important, because there are many different types of coating that are used on pipelines, ranging from 3-layer polyethylene all the way down to coal tar enamel. Not so much used these days, but there are still pipes around with bitumen on them. So we know the behavior, the long-term behavior of coatings, and they all degrade with time. It's just the speed of the degradation that's important. 3-layer PE hardly degrades at all, but fusion bonded epoxy can exhibit signs of degradation much more quickly. Doesn't mean it's a bad coating. It just means that that's the way it behaves. It takes up more moisture. The age of the pipeline is important, because that would depend how well it was originally coated, how well it was put into the ground, how careful they were when they put it in the ground. If there's any history at all of leaks, then that would raise the risk level. If there's a history of third-party damage through vandalism, or in some countries, luckily not much in this country, but in some countries you get hot taps on the pipes where people take the product, usually oil, or sometimes even they do hot taps for water in some Middle East countries. And of course, if the pipe's in a location where the access is difficult, say it's running under the M25 or running under motorways or canals or rivers, then you might rate that a little bit higher. And then the environmental factors tend to be things like electrical interference, which we covered in another presentation, but very briefly, if you recall that cathodic protection is just an electrical circuit. If you get some other electricity on it that you don't want, that can affect what's happening to the cathodic protection. And the kind of things that create a problem are overhead power lines for AC and DC these days, buried power lines, AC and DC, AC railways, DC trams, mining activities, DC from workshops where they're doing a lot of welding, that kind of stuff. That raises the risk. Third-party crossings are where other people's pipelines cross yours, and it's possible to get interaction between the two systems, so you need to take care of that. Third-party parallelisms are also a risk, especially if the third-party one is very close to an AC line and it picks up the AC. It can re-radiate that AC onto your pipeline, which can exacerbate the corrosion. Vandalism, self-evident. Environmental issues are very important these days. Bugs and bunnies always appear in the risk assessment, and if, like in the UK and most countries in the world, we have areas which are very sensitive to environmental damage. In this country, they're called sites of special scientific interest, and that's a high risk. You don't want any problems in those sort of areas. And there are some areas where the risk of losing product through a leak, the loss of reputation is so serious and furious that you you really would give that a high rating. So we've put together a very simple matrix here with some weightings on it. We've looked at the resistivity on the left, which is, it's a measure of how conductive the soil is. And if it's very conductive, then it's more likely that corrosion can occur than if it's not very conductive. So you can make up your own weightings. Indeed, you'll have to for every pipeline because they're all different. But in this little example, we've broken it up into 3 pipeline sections between 0 to 61, 61 to 71, and 71 to 81, just as an example. And at the bottom, you can see the weighting is highest for 0 to 61. So that would help to drive you to develop a routine monitoring and maintenance that suits that kind of situation. So this is just a little summary of what I mentioned earlier about the voltage and the current. And just to remind people, because it seems to be often overlooked, that it really is a very simple circuit. It's just, if you imagine you had a battery with a positive and a negative terminal on it, and you had a lamp bulb, and you connect one of the terminals to one side of the lamp and the other to the other side, and it will light up. If you take one of the terminals off, it will stop working. If you cut the cable, it will stop working. If the battery goes flat, it will stop working. So very often, the kind of monitoring and maintenance that is done is just very simple checks on the actual electrical connections everywhere. Now, one of the difficulties that you have with measuring what the pipe's doing is that it's buried, and you don't want to dig down to it every time you want to take a measurement. And the basic values that we take in an electrical circuit are electrical measurements. And for pipelines, it's the potential, the voltage that exists between the pipe and the soil. I'll talk about that in a little bit more detail later, but essentially, the majority of the monitoring analysis is done on potentials and currents. So in order to measure the potential of the pipe, during construction, we attach a cable to the pipe by brazing or welding or some other method, and we bring the cable up to the surface, and we put it in what we call a test post, which means that somebody can go to that test post, connect to the pipe via the test post, and then put a special electrode in the ground to measure the voltage. The other key elements, I think we've probably mentioned them all so far. That's the anodes, either the galvanic or the impress current, the power supplies. You may often see them referred to as a TR, which is an abbreviation for transformer rectifier, which were the very old equipment that they used to use, which transformed the AC voltage to a lower AC voltage, then rectified it to a DC voltage, and then supplied it to the pipe. So even though these days there's an increasing use for switch mode power supplies or solar systems, they still sometimes get referred to as a TR. Bonds are things where we connect to other people's pipelines or to other structures in order to balance currents out. Again, we would just do a visual check on those and a current measurement. Casings, I haven't mentioned, but sometimes when we go underneath a road, a railway, or a river, we add extra mechanical protection to the carrier pipe, and we put it in a casing, which is just a larger steel pipe. And then we pull the pipe through the casing on special supports to keep it separate from the casing. And we have to check that those casings aren't flooded or damaged. Isolation joints are just electrical resistance that we put in the pipe to break it into sections. And decoupling devices are widgets that take away the AC, which you don't want on your pipe, that leaves the cathodic protection DC on the pipe, which we do want. There are lots of standards that tell us how to assess the CP performance. I won't go through all of them, but they basically rely on potential measurements as a judge of whether or not your pipeline is meeting the requirements of the specifications. So I mentioned earlier about the pipe to soil potentials, and sometimes it's not enough to just measure them at the test posts. We do need to measure them in between the test posts. And the way we do that is to use a trailing wire to connect to the test post, and we take the measurements at close intervals. Could be 1 meter, more typically it's a couple of meters. And then to locate coating defects, we use another technique called the DC voltage gradient survey. Now the picture on the left shows you a test post, a typical UK test post. It's a concrete test post, and you can see the red wire there coming up from the pipe below. And the technician is taking a pipe to soil potential measurement using a multimeter, and you can't see it because it's hidden behind the box, but it has a reference electrode there stuck in the ground. And the picture on the right shows some data loggers at a location where there were 6 different pipelines close together. And it was necessary to measure the potentials of the pipelines at the same time. So these actual data loggers are satellite synchronized. So you know that all the measurements are synchronous, and that allows us to determine whether or not things are acceptable. This picture shows a different type of data logger, and the little orange blob at the bottom stuck in the ground, that's the reference electrode. And this little logger runs unattended for 3 years or more, depending on how often you interrogate it. It takes a reading every second, and then it sends the data at a predetermined interval once a day. Is typical, but it doesn't send all the data. In order to be economical with the battery use and the communication with the cloud, it just sends a summary of the data once a day. But if you want it, you can interrogate it, and you can download the 1 second data and do some analysis. This is just some to show you what the data presentation appears like, so that you can see exactly what's going on. In the picture on the left, you can see 2 surveys going on at the same time. The chap with the orange high-vis jacket, he's doing the close interval potential survey. And you can see at the bottom of his rucksack, there's a coil of copper wire, which is connected to a test post behind him. And as he marches along the pipeline, sticking his reference electrodes in the ground, he measures the pipe to soil potential continuously. And the data is connected to an ArcGIS system, so that the GPS accuracy is sub-meter, and the data package comes with the date, the time, whether the system's on or off, and what the actual location is. And the chap at the front is doing a voltage gradient survey, where he has 2 sticks, like the guy on the right, and he measures the gradient of the voltage going onto the pipe. And these gradients are a bit difficult to explain to non-specialists, but it's a bit like water running down a hill. If you look at a waterfall, that's a very steep gradient. If you look at a stream running down a slightly sloped pasture, that's not such a steep gradient. Well, if you could see the lines of equipotential in the ground coming from the anodes or the interference, it would look like that, like either a waterfall where you get a steep gradient or a gentle slope. And with those 2 sticks, he's able to detect that. The picture on the right shows the equipment more. That's Richard there doing a survey in some very difficult conditions, very, very hot weather, very, very dry conditions. And it's just near a dried out water course, which is known as a wadi. And Richard was looking for coating defects in that case. So the The big question is, how often do you need to look at all these test posts and do these surveys? And when we wrote the ISO 15589-1 standard, which is cathodic protection for on-land pipelines, as they like to call it, we tried to make a table to guide people. But every time we tried to do it, somebody would say, oh, well, but what if so-and-so, or what if it floods, or what if it dries out? Or so they're pretty vague, and we leave it up to the operators of the pipeline and the cathodic protection specialists to come up with the right period. But as a guide, you should look at impressed current stations 1 to 3 months. Stray current drainage stations are things where we drain off some of the current we don't want and give it back to somebody else. Foreign pipeline connections are straightforward. So that's what you would get from the standard. But in reality, you would need to tailor it to meet your own requirements. But in this day and age, where we're also environmentally aware and aware of our carbon footprint, we need to look at the implications of doing routine test post and transformer rectifier measurements, because sooner or later, somebody has to drive there. And they're nearly always in areas that aren't served by public transport, so there's no chance getting public transport and walking. So you have to drive there. And as well as the carbon footprint, there's also the very obvious increased risk of a road traffic accident. Road traffic accidents are a major feature in everybody's life. And it's self-evident that the more you drive, the more likely you are to have an accident. Now, luckily for us, the remote monitoring systems are a mature technology in cathodic protection industry. We tend to install them in the power supplies, whether that's transformer rectifier, switch mode power supply, solar powered system, thermoelectric generator. And also, if we have a pipeline near railways, which are a major source of electrical interference, we install them to monitor key potentials and currents on the railways. And they can either be powered by an internal battery or powered from the solar power system or connected to the mains. Now, the picture on the left shows an old-fashioned transformer rectifier, which is filled with oil to keep the components cool. And you change the output on it by switching it off, unbolting a metal link, a copper link between different terminals, and then connecting them up again and seeing what happened. Very coarse, but they are still in operation. Some of these are 60 years old and still working fine. Sadly, they're hardly ever maintained properly. The oil deteriorates with time, and it should be tested with what's called a crackle test, actually, for its dielectric strength and cooling properties. The small widget you can see there is a silica gel breather, which is intended to remove the moisture from any air that is sucked into the unit due to the different differential air pressure. That needs to be changed regularly. The one on the right is a modern equivalent that it replaces the one that you see on the left. This unit here is a remote monitoring and remote control unit. This is the antenna that it communicates through. This is a switch mode power supply, and this unit controls the output of the switch mode power supply. So if you want to operate it in a constant current mode, you can. If you're suffering from changes in soil conditions or electrical interference, you can make it operate automatically to maintain the potential and the current stable. There's another example of a very old transformer rectifier here, where this knob is connected to a big transformer, a rotary transformer. And as you turn it round, you increase or decrease the amount of AC, and then it rectifies it. And this remote control unit was installed retrospectively on this. So the output from this is now controlled by this unit here, which you can operate remotely. And this again is the modern equivalent with the the unit displaying the pipe to soil potential and the voltage out from this unit here. And this blob that you can see here is surge protection to protect it from lightning damage. So the task for the remote monitoring unit is you should be able to do everything remotely that you could do if you were in front of it in terms of controls. I'm not talking about stripping it down, obviously. And you need to be able to increase or decrease the output, start the unit to switch on and off, which is something we have to do for close interval potential surveys and DCVGs, and also for interference studies. And there is also a little contact on it that you can rig up. So if somebody opens the enclosure door, you get an alarm sent to somebody. Typically, they record a measurement every second, but they can be remotely programmed to record as often as you like, even to fractions of a second for some units. And they're all satellite synchronized and can be connected to remote units. This is a snapshot I took yesterday of a remote control unit, which is in service in the UK in this case. And what I wanted to draw your attention to was that this is almost real time. About every 5 minutes, it sends another block of data. So if you want to see the effects of any changes that you're making to this or something else, you'll see them very quickly. And you can display this on your mobile phone if you're on site. This blue line here is the current output from the unit. You can see it's varying like fury. And the reason it's doing that is because this system suffers from electrical interference. And what we want is to maintain that red line there stable. So that red line is maintained in that stable state by the movement of these current outputs. So it's a kind of an automatic feedback system, and it means that you can rest assured that everything's working fine. The other thing that you can do with the same unit is you can set up the switching periods you want. You can decide what mode you want it in, either measuring, switching, disconnected or connected. And you can tell it if you want it to control by the potential, which this one does. So you set the potential that you want it to operate at, which in this case is -1.6. And for people who are involved with cathodic protection, they might think that's very negative, but that includes a huge measurement error because the electrode is in a big electric field from the ground bed. So from tests, we know that that will result in the right potential. And then you can see the status of the battery. This one's powered by mains and it's still got an internal battery. So if the mains fails, you still get the data. And we also monitor the temperature of it, so we can see how things are behaving. So the benefits of remote monitoring are reduced carbon footprint, continuous monitoring of the data. So it doesn't matter whether they say 1 year or 3 years, you're monitoring it all the time. And it can be remotely controlled. That's a huge benefit. And the ArcGIS system I mentioned that's used on the surveys is a marvelous thing because it gives sub-meter accuracy and allows live tracking and data reporting of the surveys. So you as the client can look at any time and see where the monitoring team is and what they're doing. And you can immediately click on the map, which is an excellent visualization, and you can see what results they're getting. So it's a very good way of tracking people. So I'm conscious of the time, I've run over a little bit, but the summary, the first thing you need to do is create a priority matrix, get your house set out right, get everything sorted, minimize the carbon footprint by using remote monitoring and control, and optimize the reporting using an ArcGIS reporting platform. So that's been a very quick gallop through the remote monitoring of a cathodic protection system. There's an awful lot of stuff that can be discussed, but I think from this, you should have a good idea of what's involved. and why the CP guy keeps coming and bothering you to get access to go and do stuff. So that is all I have. Thank you very much for attending the presentation. I do hope it's been of some use to you. I know that Gosia works very hard to promote these things, and this is the 6th one that she's done. So congratulations to Gosia. Any questions? I'll be happy to take them now, Gosia.
Yes, thank you very much, Ken and Richard, for preparing and delivering another very interesting presentation on CPE, and for your continuous support to the Southeast branch. You know, like, as you've mentioned, you've done 6 of those presentations, and we're hoping for more of those because they are extremely popular, and we know that people watch them on YouTube channel. So yeah, thank you very much. Now questions. There is one question. I'm conscious that Richard has replied to that question, but then I think if we don't repeat it on this recorded call, people won't see it. So let me read it out. So the question is this. Let me just go there. Okay, the question is this, by Fahim. If we have 2 pipelines in row protected, same CP system, if these pipelines cross at some stage, will there be any interference and need for bonding? So I know what Richard has responded. Richard has responded, if they are protected by the same CP system, then no, there will be no further interference between them at the crossing point. No additional bonding would be required. If they are an independent CP systems, that would be different. Have you got anything else to add, Ken?
No, I don't know if Richard would like to elaborate on that.
Yeah, or Richard?
No, probably not.
No.
No.
Any other questions from the audience?
Hi, yeah, it's Ian. Just got one quick question. If the any part of the protected main had a repair put on it, like a metal encasing, what we call a metal encapsulation, would that affect the CP at all, or would that have to be altered?
Yes, thanks, Ian. That's a very good question. Yes and no. It depends whether or not it's coated or if it's just bare. If it's bare, that will represent an increased drain on the cathodic protection current system, and there may not be enough current to go around, in simplistic terms, to protect the other defects. So if you had a small coating defect half a meter away, that might not be protected because all the current's going to the big one. But one of the classic mistakes that does happen is when people put a pup piece in, or if they cut out a bit of pipe and put a new piece of pipe in, and then they come back a bit later, a few months later, and say, well, this new steel is terrible because it's already corroded, whereas the old stuff's still doing great. And the problem is that new steel has a higher energy than old steel. It sounds silly, I know, but it does. And the new steel, which is a small piece, acts as an anode to the old steel, which is a big piece. So when you put a new piece of pipe in, you have to be meticulous in the way that you recoat it and how you not just quickly throw a few turns of sticky tape over it. You really need to do a very good job on it, and then make sure that that system that you've selected to do that coating is good for the remaining life of the pipe. Coatings are like anything else. You get what you pay for. And if you only pay a few shillings, give my age away, you only pay a few pennies for it, you can't expect it to perform as well as a proper high quality, long lasting tape or coating system. I hope that answers your question, Ian.
Yeah, it does. Yeah, thanks very much for that. Thank you.
Any other questions? well, if not for now, if anyone has got questions, you've got email addresses, you can contact Ken or Richard directly. And then, yeah, so thank you very much again to Ken and Richard. That was very good and interesting.
There is another question that's come up.
Is
there?
there? Sorry, I
Could
missed that.
protection be extended to chemical storage tanks, which
That's
are part
right.
of the system, or is this only suitable for pipelines? Okay, I don't know if you're still on the line, Helen. Are you still with us? No, possibly not. Okay.
No, but if you answer, she can watch it back on YouTube.
Okay. It depends whether the tank is buried or whether it's above ground. Generally speaking, tanks tend to be earthed for safety reasons, and therefore it's better if they are isolated from the pipe, electrically isolated from the pipe. If that's not possible, there are other means that we can employ, but they're a little bit complicated, but it can be done. I hope that answers that question. Helen, to everyone, yes. Oh, does that mean you're still on the line, Helen?
Yeah, maybe she's muted.
Okay.
Yeah.
Okay.
Right. I'm checking chat whether I don't miss more questions, but I think
did that answer your question, Helen? Or do you need anything more?
Yeah, maybe Helen is on mute and cannot.
Okay. Well, you could answer in the chat if you need anything else, Helen.
Anything from anyone?
No, I think not, Gosia. Well, thank you everybody for sitting through it.
Yeah, thank you very much. Again, Ken, Richard, and thank you all for joining. As Ken said, this presentation, along with others, they are available on PIG's YouTube channel. Please do look on the events side on PIG's website, because there are lots of presentations and events that are coming up. So yeah, please do look there and register. So thank you very much and have a nice afternoon.